So we have studied what is center of mass. What is center of mass? The point at which the entire mass of a body is supposed to be concentrated is called the center of mass. Now we can discuss what is center of gravity. It is the point at which entire weight of a body is supposed to be concentrated is called the center of gravity. For example, take an irregular shaped cardboard and a narrow tipped object. So this is a irregular shaped cardboard and this is the pencil. Narrow tip object like a pencil. You can locate a point on the cardboard where it can be balanced. So that cardboard can be balanced at a particular point using the pen or pencil, isn't it? This point of balance is the center of gravity. So the point at which the total mass or total weight of that cardboard is supposed to be concentrated, that point is called the center of gravity. So in the case of cardboard, at a particular point that cardboard can be balanced. Okay, and that point is the center of gravity. The tip of the pencil provides a vertical upward force. So this is the point at which the cardboard is balanced. So this is actually the center of gravity. So at that point, the pencil exerts an upward force. Okay, so the pencil or the pen, the pointed object exerts an upward force, that is the reaction, normal reaction. So tip of the pencil provides a vertical upward force due to which the cardboard is in mechanical equilibrium. So it is at rest. So that at that point the cardboard is at rest. Using that external force or using that pencil, the cardboard is balanced. So upward force is acting, the vertical upward force is acting on the cardboard at the point. The reaction of the pencil is equal and opposite to the weight. So at that point two forces are acting. Weight is acting in the downward direction and the tip of the pencil exerts a normal reaction in the upward direction. Both the forces are equal and opposite, hence net force is equal to 0. That means the system is in mechanical equilibrium, translational equilibrium. Okay. Now the system, it is also in rotational equilibrium. The system is in translational equilibrium as well as in rotational equilibrium because the cardboard does not rotate. So at that point it is at rest. Using that pencil and the cardboard, we can balance that cardboard, means the cardboard is at rest. So no external force is acting, no external torque is acting. So it is in rotational equilibrium as well as in translational equilibrium. So here weight is acting in the downward direction, normal reaction is acting at the upward direction. So both the forces are equal and opposite and hence that point is called the center of gravity. So hence center of gravity is also defined as the point where the total gravitational torque on the body is 0. Total gravitational torque means no external force is acting there, no torque is acting there. So total gravitational torque on the body is 0 and that point is called the center of gravity where the total weight of the object is supposed to be concentrated. Okay. We are going to introduce a new term, moment of inertia, which is represented by the letter I. Moment of inertia. Moment of inertia is the rotational analog of mass. So in linear motion we know what is mass. Similarly in rotational motion the analog is moment of inertia. Moment of inertia is the rotational analog of mass. What is this moment of inertia? Consider a rigid body which is rotating about a given axis. This object is rotating about a given axis. Consider a small particle of mass m which is at a perpendicular distance r from the axis of rotation. Now the moment of inertia is given by, of the particle moment of inertia is given by I equal to mr square, where m represents the mass of the particle, r is the perpendicular distance of the particle from the axis of rotation. So moment of inertia is defined as product of mass and the square of the distance, perpendicular distance between the particle and the axis of rotation. So that is called a moment of inertia and its SI unit is mass into distance square, no? So kilogram meter square. Okay. Now we can derive the kinetic energy of a rotating body in terms of moment of inertia. Consider a rigid body which is rotating about a given axis with constant angular velocity omega. So this is same object. Consider this rigid body rotating about a given axis. AB is the axis and it is rotating with an angular velocity omega. This is rotating with an angular velocity omega. We know kinetic energy of the body. The total body kinetic energy is given by half mv square. Since this body consists of a number of particles, infinite number of particles, we can take the total kinetic energies, we can take the summation. Kinetic energy is half summation of all mass into the velocity of all the particles, linear velocity of all the particles. So we can write total kinetic energy is half sigma mi vi square. Okay children, so here we can take the summation I is equal to 1 to n number of particles are there. So total kinetic energy is half sigma I equal to 1 to n mi vi square. And kinetic energy can also be written as kinetic energy k equal to half sigma mi. Here we have taken velocity vi. Now velocity can be expressed in terms of the angular velocity omega. We know v equal to r cross or v equal to r omega, omega cross r, v equal to omega cross r. So using that we can write kinetic energy half sigma mi ri omega the whole square. Velocity v can be written as r omega square. Velocity v square can be written as here v square can be written as vi square can be written as ri into omega the whole square, or k equal to half sigma. Here also we can put I equal to 1 to n mi ri square into omega square. But what is the sigma mi ri square? Sigma. So for a single particle we can write moment of inertia is mi square. For n number of particles we can write I equal to sigma I is equal to 1 to n mi ri square. Okay, for single particle mr square, for n number of particles we can write sigma mi ri square. Clear? So here also sigma mi ri square is actually moment of inertia. So kinetic energy is given by the formula half I omega square. So kinetic energy of any body rotating about a given axis is given by, that rotational kinetic energy is given by half I omega square. The object is rotating with angular velocity omega and the object having moment of inertia I. So kinetic energy is half I omega square. We have the expression for kinetic energy of a body in linear motion. We know linear kinetic energy is given by half mv square, whereas rotational kinetic energy is given by half I omega square. We can compare it. Here mass in linear motion, corresponding term in rotational motion is I. Therefore it is called a rotation analog of mass. Okay, here in linear motion mass, in rotational motion moment of inertia. In linear motion velocity, in rotational motion it is angular velocity. Okay children, so rotational kinetic energy of any object, any rigid object rotating about a given axis is half I omega square. Derive the formula for angular momentum of a rotating body in terms of moment of inertia. We have angular moment L equal to r cross p is equal to r cross, what is momentum? Momentum is mass into velocity, isn't it? It can be written as r cross m into, but velocity v equal to r omega, isn't it? So v equal to r omega. So this can be written as m r square into omega. So angular moment L is equal to m r square into omega. So total angular momentum can be written as total angular momentum. Total angular momentum is L equal to, we can take the summation. This is the angular momentum of a single particle. For n number of particles we can take summation I is equal to 1 to n mi ri square into omega. But we know what is sigma mi ri square, but sigma mi ri square, what is that called? Moment of inertia I. Therefore the total angular momentum L equal to I omega. So the relation between angular momentum, moment of inertia and moment of inertia is L equal to I omega. Okay children, so the relation between angular momentum and moment of inertia is L equals I omega, direct relation. First you take L equal to r cross p, put MP, momentum P equal to mv, but V equal to r omega. So it can be written as mr square into omega. So total angular momentum, if you summation, put the summation mi square into omega. What is sigma mi square? That is moment of inertia. So angular momentum L equal to I omega. The relation between torque of a rotating body in terms of moment of inertia. Relation between torque and moment of inertia. We have torque tau equals R cross F, and tau can also be written as R cross F equal to, from Newton's law, F equal to ma, isn't it? So tau equal to R into ma. And what is this acceleration? We know the relation between acceleration, or first we can write the relation between velocity and angular velocity is V equal to r omega, isn't it? We can just differentiate it dv by dt, differentiate with respect to time. dv by dt is equal to r into d omega by dt. What is velocity by time? That is called acceleration, is equal to r into what is angular velocity by time? That is called angular acceleration, which is alpha. Okay, linear velocity by time is linear velocity divided by time is acceleration. Similarly, angular velocity divided by time is angular acceleration. Here alpha is called angular acceleration. It is the acceleration in rotational motion. Okay, so here we can write equals r into m into acceleration. What is acceleration? R alpha. So torque tau equal to r into mr into alpha. So it can be written as mr square alpha. This is the torque corresponding to a single particle. So the total torque, how will you find out the total torque? We can summate. I is equal to 1 to n mi ri square into alpha. What is sigma mi ri square? That is moment of inertia I. So torque tau equals I alpha. So the relation between torque and moment of inertia is tau equals I alpha. Start from the formula, tau equal to r cross f, but f equal to ma, and acceleration a is equal to r alpha. How? Because velocity is r omega. Just differentiate velocity with respect to time. So dv by dt equal to r into d omega by dt. Velocity by time is acceleration. Similarly, rate of change of angular velocity is angular acceleration alpha. So a equal to r alpha. Using this, we can write acceleration is r alpha. So we can write tau equal to m r square alpha. Total torque is given by, we can summate. So sigma is equal to 1 to n mi ri square into alpha. So it is I alpha. So the relation between torque and moment of inertia is tau is equal to I alpha. Relation between angular momentum and moment of inertia is L equal to I omega. Here torque is given by, in rotational motion tau equal to I alpha. In linear motion, what is the corresponding torque? Force, isn't it? F equal to, instead of moment of inertia there it is mass. Instead of angular acceleration there is acceleration. Okay, so torque in rotational motion, force in linear motion. Moment of inertia in rotational motion, mass in linear motion. Angular acceleration in rotational motion, acceleration in linear motion. Okay children? Now we know law of conservation of angular momentum. What is law of conservation of angular momentum? If external torque equal to 0, angular momentum remains a constant. That means we have tau equal to dl by dt. Torque tau equal to rate of change of angular momentum. If external torque equal to 0, what happens to momentum? It remains a constant. And we know angular momentum is equal to I omega. That means I omega remains a constant. So this is another form of law of conservation of angular momentum. Already we have studied, if tau equal to 0, angular momentum remains a constant, or we can say that I omega remains a constant. Now we can see some examples relating law of conservation of angular momentum. An ice dancer stretches her arms to increase the moment of inertia, thereby decreasing the angular velocity. By folding her hands, what happens? Angular velocity increases and moment of inertia decreases. A circus acrobat and a diver also take advantage of this principle of law of conservation of angular momentum. Comparison of translational and rotational motion. In linear motion, displacement is x, while in rotational motion, angular displacement theta. In linear motion, velocity v, which is dx by dt. In rotational motion, angular velocity omega. In linear motion, acceleration. In rotational motion, angular acceleration alpha. In linear motion, mass, while in rotational motion, the corresponding term is moment of inertia. In linear motion, F equal to ma, and in rotational motion, tau equals I alpha. In linear motion, work is equal to force into displacement, Fs. In rotational motion, work W equal to tau into angular displacement d theta. In linear motion, kinetic energy is half mv square, while in rotational motion, kinetic energy is half I omega square. In linear motion, power equal to force into velocity Fv, while in rotational motion, power equal to tau into omega. In rotational motion, angular momentum is L equal to I omega, while in linear motion, linear momentum is mass into velocity. So this is the comparison between translational and rotational motion.